Chapter 4, Exercise 5. Hints. Define an extension of g of the function f as a linear function on all intervals that constitute the complement of e. Exercise 229. Prove continuity of g by showing the equality here. Definition 425 for all p in R. To extend the result to vector-valued functions, use Theorem 410. Solution. The complement EC is an open subset of R, Theorem 223. By exercise 229, the complement EC is a disjoint union of an at most countable family of intervals here. We note that endpoints AK and BK belong to the set E whenever they are finite. Indeed, if a left endpoint AK is a real number that does not belong to E, then there exists an index, j not equal to k, such that aj less than ak less than bj. Consequently, this, which is impossible. Similarly, bk element of E whenever a right endpoint bk is a real number. Now, we will define an extension of f on each interval ak, bk exclusive. Case 1. If ak equals minus infinity, bk equals positive infinity for some k, then EC equals R and E equals empty set. The domain of f is empty, so any continuous function g here, that is, g of p equals 0, is a continuous extension of f. In what follows, we discard this case. Case 2. If this, we define g of p equals f of ak, ak less than p less than positive infinity. Case 3. If this, then we define g of p equals f of bk, negative infinity less than p less than bk. Case 4. If this, we define the following. Case 5, finally, we define g of p equals f of p for p in E. We will prove that the function g is a continuous extension of the function f. Step 1. By definition, g, here, is an extension of f, case 5. Note that the function g is continuous on the complement, here, by construction. G is linear on each interval ak to bk exclusive. At every real left endpoint ak, the right-hand limit g ak plus exists and is the following. Cases 2, 4, 5. At every real right endpoint bk, the left-hand limit g bk minus exists and is the following. Cases 3, 4, 5. See definition 425 for the notion of one-sided limits. It remains to prove that g is continuous at every point p in E. In what follows, we consider a point p in E. Step 2. We will show that the right-hand limit g p positive exists and the following. If the point p coincides with one of the left endpoints ak, then the needed relation was already proved. Step 1. During step 2, we assume that this. Auxiliary statement. If this, for some index L, then p less than AL. Note that p does not equal to AL by assumption. If p greater than AL, then this, which contradicts the fact that p is an E. The statement is proved. Let epsilon be greater than 0. Since f is continuous on E, there exists delta greater than 0, such that for any point here, we have the following. There are two possibilities. Possibility 1. For some alpha greater than 0, this, let the following. The definition of g, case 5, and the choice of delta imply this. Possibility 2. For any alpha greater than 0, this, there exists a number here. For some index k, r element of ak to bk exclusive. By auxiliary statement 1, p less than ak. Note that p less than ak less than r less than p plus delta. Consider a point here so that p less than q less than ak less than p plus delta. If q and e, then by choice of delta, the following. Assume that q not element of e, then q element of aj to bj exclusive for some index j not equal to k. By auxiliary statement 1, we have the following. Then bj greater than ak, then this, which is impossible. We'll call that aj less than q less than ak. So, this. By choice of delta, this and that. By construction, g of q equals this. Consequently, we have the following. And continuing, in each possibility, there exists some gamma greater than 0 such that this, for all q in p to p plus gamma exclusive. Relation g of p positive equals g of p is proved. Step 3. We will show that the left-hand limit gp negative exists and the following. If the point P coincides with one of the right endpoints bk, then the needed relation was already proved. Step 1. Doing step 3, we assume that this. Auxiliary statement 2. If this, for some index L, then BL less than P. Note that P not equal to BL by assumption. If P less than BL, then this, which contradicts the fact that P and E. The statement is proved. Let epsilon be greater than 0. Since f is continuous on E, there exists delta greater than 0, such that for any point here, we have this. There are two possibilities. Possibility 1. For some beta greater than 0, this, let this. The definition of G, case 5, and the choice of delta imply this. Possibility 2. For any beta greater than 0, this, there exists a number here. For some index k r element of ak to bk exclusive. By auxiliary statement 2, bk less than p. Note that p minus delta less than r less than bk less than p. Consider a point here so that p minus delta less than bk less than q less than p. If q element of E, then by choice of delta, this. Assume that q not element of E. Then q element of aj to bj exclusive for some index j not equal to k. By auxiliary statement 2, this. If bk greater than aj, then this, which is impossible. We'll call that bj greater than q greater than bk. So, this, by the choice of delta, this and that. By construction, g of q equals this. Consequently, we have the following. And continuing, in each possibility there exists some gamma greater than 0 such that this, for all q in p minus gamma to p, exclusive. Relation g of p negative equals g of p is proved. Conclusion. For any point P and E, we have this. The function g is continuous at any point P and E. From step 1, we have that g is continuous at every point P and EC. This implies that the function g is a continuous extension of f. Extension to vector-valued functions. Let the set E subset of R be closed and the function f here be continuous. Then there exists a continuous function g here such that g of x equals f of x for all x in E. Proof. Let f of x equal this x element of E where each function f of j is this, is continuous. See Theorem 410. From the one-dimensional case, that is k equals 1, we know that there are functions gj here such that for each j element of 1 to k, gj is a continuous extension of fj. Define a function g here as g of x equals this. The function g is continuous by Theorem 410. For all x in E, we have the following. It follows that g is a continuous extension of f. Comments. A continuous extension g here of a continuous function f here, where E is a closed subset of I, is not unique. As an example, consider a continuous function f here, given by f of x equals 1. An approach suggested in this exercise gives a continuous extension g of f as g of x equals 1, x element of real number. Another continuous extension of f is given by a function h defined by h of x equaling this. Here is a figure, two distinct continuous extensions of f. If the domain E of the function f is not closed, the result may fail. As an example, let the domain be E equals this, and the function f here be defined by f of x equals cosine 1 over x, x greater than 0. Such function cannot be extended to a continuous function g here. Indeed, consider sequences Tn equaling this, Sn equaling that. We have the following. Since this, the limit f0 positive does not exist. Results of this exercise can be generalized to the case when the domain of a continuous function f is a closed subset of some metric space x. Namely, if x is a metric space, E is a closed subset of x, and the function f is continuous, then there exists a function g, which is a continuous extension of f. This result is known as the Tietze extension theorem. If the range of f is replaced by arbitrary metric space, the result of this exercise is no longer true. As an example, consider the set here and a continuous function here. Here z is the space of all integers with the usual distance. If g here is a continuous extension of f, then g of 0 equals 0, g of 1 equals 1. Theorem 423 implies this, which is impossible. It follows that f has no continuous extension with values in z. Thanks for watching.